Hey guys, Pankaj here. Welcome back. Today I'm going to talk about a very important topic in statistics, that is nothing but Box-Cox transform. Okay, so what is this transform? Why we use? Where exactly we use it? Okay, so let me share my desktop and I'm going to explain the complete theory with the help of whiteboard, as well as I'm going to prove the theory with the help of Python programming. So let me share my desktop. Okay, so yeah. So we have seen the Gaussian normal distribution, right? Gaussian normal distribution. So what exactly this was telling? Basically, any data which is having mu, that is nothing but your mean, 0, and variance is nothing but 1, and which exactly looks like bell curve. That is nothing but your Gaussian normal distribution. Okay. What about data where the data is basically skewed? So we have seen, right, in distribution, like what kind of skewed data is there, whether this will be like right skewed, and you will have something called like this, that is nothing but left skewed data. Left skewed data. Okay, this is also called negative skewed data. This is called positive skewed data, right? So whenever you have this kind of skewed data, this is not assumed to be a normal distribution. Okay, so in machine learning, once we talk about machine learning, right, it is very much assumed that you have given a data which is very much normally distributed, means it is exactly following this kind of curve, bell curve. Why it is assumed? Because once you know like your data is Gaussian normal distribution, you know very good principle about empirical theory we talked, right, where if data is normally distributed, then mu equal to 0 and sigma 1, 2 and 3, then exactly what to say, your 68% data will be lying from mu plus minus 1 sigma, correct? And 95% data will be lying between mu plus minus 2 sigma, and 99.7% data will lie between mu plus minus 3 sigma. Okay, in case your given data is normal distributed, where mu equal to 0 and sigma equal to 1. So whenever you don't have any data which is not normally distributed, these kind of inference you cannot what is it derive, right? Because this is what you will be able to derive, or you will be telling about the data so much just by assuming that your data is normal distribution. But what if it is not normally distributed? So there is something called Box-Cox transform. Okay, so what this Box-Cox, those two person who developed this particular, like George Box, and there's one more name, some Cox. Okay, so they derived a formula by which you can transform any data which is not following Gaussian normal distribution. Let's say in this case, this is positively skewed or right skewed, or this is negative skewed or left skewed data. You can convert them into Gaussian normal distribution with the help of Box-Cox transform. Okay, so we'll see how we can do with the help of Python. So after applying Box-Cox, it is going to be a transform. So let's say you have some data x equal to x1, x2, x3, and so on, xn, correct? And let's say this is nothing but non-Gaussian, I'll mention. Okay, and now let's say you have y, where y1 and y2, y3, and so on, yn, correct? And this is nothing but Gaussian normal distribution data. So this x, which is not a normal Gaussian distribution, you want to transform into y form, which will be basically become Gaussian normal transform. Okay, or Gaussian normal distribution data. So what we do, basically, you apply Box-Cox transform of x. It is going to provide a data, let's say x hyphen, where x1 xi, basically the first data, will be power of your lambda minus 1 divided by lambda. Okay, so this will be 2 only when your lambda not equal to 0. Okay, otherwise natural log of xi if lambda equal to 0. Okay, so this is the formula they have derived. Okay, so we will be talking about how lambda is basically returned. Okay, so there is a big formula and big mathematical calculation behind this, so that is out of scope of this video. But I'll tell you, with the help of Box-Cox, it is going to internally calculate the x bar, which is nothing but following the Gaussian normal distribution, and it will provide you the lambda value also. Okay, at what lambda value your data is getting transformed into exactly Gaussian normal It may not be exactly, but it will be very much approximation, which is going to follow the Gaussian normal distribution. Okay, so that's what is this Box-Cox transform. So let's see how to do that. So as usual, I'll be importing library called numpy, snp, matplotlib, cbound, and scipy.stats. In this we have probability plot, right, and Box-Cox. Okay, so okay, let me show one more time. I think in the past video I talked about qk-plot, right? What it was doing. So let's say if you have any data to make sure it is following the Gaussian normal distribution or not. So you will be plotting quintile of Gaussian normal distribution, and with respect to this, you will be plotting Gaussian, quantile plot of other distribution. I would say other distribution which is not a Gaussian distribution, and you want to make sure that whether it is coming from Gaussian normal distribution or some other distribution. Okay, so what it does basically, they will be having this exactly diagonal line. Okay, and let's say whatever data you have, quantile plot of this, whether it is overlapping in this line or not. Once you plot this QQ plot, you may see some data will go here, some data will be diverted from the main line. Okay, so when this kind of thing happens, means it is not a Gaussian normal distribution. But let's say the moment you plot, let's say this particular graph, let me make it big, and it is exactly following this particular Gaussian distribution, and it is overlapping exactly this particular line, means it is coming from Gaussian normal distribution. Okay, so after Box-Cox transform, we are going to plot this QQ plot also and see whether it is following the Gaussian normal distribution or not. If you see overlap, means it is a Gaussian normal. If it is not overlapping, means it is not a Gaussian normal distribution. It is coming from other distribution. Okay, so we can prove with the help of QQ plot as well as KD plot. So let's say earlier your data was like this. Okay, it is right skewed. Correct. After applying Box-Cox, if your data is exactly looking as bell curve, means it is nothing but Gaussian normal distribution. Okay, so this is what I'm going to prove with the help of Python. So we'll be using prop plot, which will help you to generate QQ plot from any given data, and Box-Cox is the probability function which will provide you the transform value of any given data, any random data, and lambda value of that particular data. Okay, by which if you apply that lambda onto that data, the original data, it is going to be start following the Gaussian normal distribution. Okay, so let's run this. Okay, please ignore the warning because it is giving maybe some version got updated, that's why. Okay, so what I'll do, I'll just generate some data from np dot random dot, let's say I'm taking some exponential data. What it takes is scale 1.0 and size I'll take, let's say 500. Okay, after taking this value, let's plot the SNS dot KD of A. Okay, so what do you see here? It is definitely a positive skewed or right skewed data, correct? So this skewed data, the moment you see, it is definitely not following the Gaussian normal distribution. So how you can say it is not following the Gaussian normal distribution? By looking at the KD plot, because it is right skewed, okay, or it is positively skewed, positive skewed. Okay, so I'll do QQ plot of this with respect to your Gaussian normal distribution. If your data is overlapping in the middle line, means it is Gaussian normal. If it is not overlapping, it is a other distribution. Okay, so how we can do that? We had this probability plot, and I want to have probability plot of this A. Just write that array, and with respect to, we already have seen, right, distribution equal to normal. This is nothing but a Gaussian normal distribution. Okay, and we'll using this plot. So I'll just use plot equal to PLT. Okay, PLT dot show. So let's see what it is. See here, it is definitely very much skewed data, and it is not at all Gaussian normal distribution, because this blue line is not at all overlapping on the red line. Okay, so which clearly tells it is not a Gaussian normal distribution. Now I'm going to take the same data and apply the Box-Cox transform, and let's see what it does. Okay, so apply Box-Cox. to transform non-Gaussian data to Gaussian normal distribution. Okay, so let's see how it can be done. So we have direct function Box-Cox, and what it takes basically array, which is nothing but your A array, which we have created. And lambda, since we are going to calculate, we don't know upfront, right? So I'm not going to give anything. It is going to have the best fit line, and accordingly to find out like which particular lambda is there. Okay, alpha, don't worry about this. Let's leave it. And optimizer also don't leave. I mean, just leave it as it is. So just provide the data which is going to be transformed. Okay, so it is going to return the transform value, which I'll use at tr, and the lambda I'll just mention lamb. Okay, so let's use this, and after that I'm just going to plot sns dot kd plot of tr. Let's see what happens. Okay, you see the magic here. Earlier your original data was right skewed. Okay, it could be left skewed also, but right now whatever sample we have taken, it is positive skewed or right skewed. And after applying Box-Cox, you see here what normal distribution says. Your normal distribution says it has to be exactly bell curve, where mean will be 0 and variance will be 1. The moment you got this right, you see here, your mean is exactly lying exactly at the 0, and your standard deviation is exactly 1. Okay, now the moment you got this, you can clearly tell. Let me just use different color here. The moment you got this right, you can clearly tell, okay, my mean is exactly at 0. So I can tell my 65% or 68% data is lying between this mu plus minus 1 sigma. Okay, mu plus minus 1 sigma. Okay, now if I talk about this, where mu is your minus 2, like plus minus 2, right? So whatever data you see here, I can clearly say mu plus minus 2 sigma, your 95% data is falling under this, and here it is 68%. Okay, and the another one is nothing but your minus 3, plus minus 3. So whatever data you have here, because now we know empirical rule of Gaussian normal distribution, right? With the help of this, I can tell my 99.7% data falls between mu plus minus 3 sigma. And that is the beauty of Box-Cox transform. It is going to transform the given data, which is not Gaussian normal. It will transform into Gaussian normal. And the moment you have Gaussian normal distribution, you can blindly tell, okay, my 68.5% data will be falling between this. 95% data will be falling from here to here. And 99.7% will fall between mu plus minus 3 sigma. And not only this, you can apply a lot of other statistical function on the normal data. Okay, and that is very important factor or very important reason we should use Box-Cox. Okay, and because in machine learning, once we talk, right, we will get to know it is very much assumed that your given data is a Gaussian normal distribution. That's how all other statistical method or machine learning algorithm will work on only normal distribution, no more assumption. If it is not following Gaussian normal, you need to transform, then apply all statistical function. Okay, so I hope it is clear. Now after KD plot, what I can do, I'm going to do the QQ plot also. Okay, so probability plot, plot of TR, and plot equal to PLT dot show. Now you see the magic. You see how beautifully it has transformed. Earlier it was not at all Gaussian normal distribution. After that, you see here, it is very much like almost except 99. You see this, right? This part is nothing but your 99th percentile, because this is the last value, right? In this we have the percentile from 0 to 100. Okay, or maybe 1 to 100 you can say. So this is the last value, so this I can say this is 99th percentile value. Okay, and this is 100th percentile value. Okay? So only 2 or 3 data is not at all overlapping in the what to say in the middle line. Okay, but as I mentioned earlier also, as you grow or as you increase the number of samples, right, your data will be exactly falling in the line. So here if you see, I have taken exactly around 500 samples, right? You can increase 5,000. Okay, so let's make this and run the whole thing. See the magic. You see here, almost this data, this is not falling. Again, you increase the sample, this may also fall exactly in the middle line. So your complete data will be transformed into Gaussian normal distribution. Okay, so I hope you guys liked about this, because this is going to be very helpful once we start learning machine learning and apply or learn any other statistical method. This will be playing a very important role. Okay guys, so yeah, that's all about Box-Cox transform. And yeah, if you have not understood any concept, let me know in the comment box. I'll definitely help in the next video. Okay, please download the notebook from Jovian, Google Drive, or GitHub. Try with the different particular data, modify the parameter basically, and see how your QQ plot looks like, and after transforming, how your KD plot looks like, whether it has been transformed or not. So by looking at the KD, you can clearly tell my mean is now at 0 and standard deviation is 1. Okay, but here you see this is completely different. Your mu is somewhere else, mean is almost different, correct? So this is going to be very helpful. Okay, so that's all for today. See you in the next video. So those who have not subscribed my channel, please do subscribe, share with your friends, and let them also learn. Okay guys, thank you so much. Bye bye.